You know, every software engineer has been there. You're looking at the logs, and a system is just screaming the same error message at you over and over and over again. So how do you cut through all that noise? Well, today, we're going to design a logger rate limiter to do exactly that.
Just picture it for a second. A critical error is, well, critical, but seeing it 1,000 times a second, that's not helpful. That's just noise. Our goal here is to design a really smart filter, a rate limiter, that lets that crucial first message through, but then tells all its identical twins to just quiet down for a little while. So, here's our game plan. First, we're going to clearly define this message spam problem. Then we'll lay down our one core rule, the 10-second memory rule. After that, we'll pick the perfect data structure for the job, walk through an example to see it in action, and finally, break down why this solution is just so darn efficient.
All right, first up, the message spam problem. Let's get super clear on what we're actually trying to build here.
What we're really building is a logger class, and it's going to have one key job, one function, should print message. This function will take a message and a timestamp and give us a simple yes or no. True if we should print it, false if we should just ignore it. Basically, we're trying to stop our system from being way too chatty.
So, how does it make that decision? How does it know when to say yes or no? Well, the entire system, the whole logic, is built around one single, beautiful, simple rule.
This right here, this is the heart of our rate limiter. If we print a message, let's say something like database connection failed, we absolutely do not want to see that exact same message again for a very specific amount of time.
10 seconds. That's it. That's our golden rule. The moment a unique message gets printed, it kicks off a 10-second cooldown. Any identical messages that show up inside that 10-second window, they get dropped. Simple as that.
And here's what that looks like over time. Let's say a message, we'll call it foo, gets printed at some timestamp we'll call t. Instantly, the system puts up a block. No more messages that say foo are allowed until the clock hits t plus 10.
Now, this whole 10-second rule implies something really important. Our system needs a memory. It has to remember two things for every unique message it sees. One, that it was printed, and two, when it was printed, so it knows when the cooldown is over.
So, the crucial insight is this need for a super fast lookup. When a new message comes flying in, we can't waste time scanning through a giant list of every message we've ever seen. We need an answer, and we need it now. And that requirement points us directly to the perfect tool for the job.
And that perfect tool is the hash table, or if you're a Python person, you call it a dictionary. Think of it like a super efficient phone book. The message itself is the name we're looking up, that's our key, and the next time it's allowed to be printed, that's the phone number we get back, that's our value. This data structure was literally made for this kind of instant lookup.
This simple tool simplifies our entire logic down to a really easy two-step check. A message comes in. We look it up in our hash table and ask one question. Is the current time before the allowed time we have stored? If it is, nope, we reject it. But if the current time is at or after the allowed time, we say yes, print it. And this part is absolutely crucial. We immediately update the table with the new next allowed time, which is just the current time plus 10.
Okay, theory is great and all, but let's actually see this thing work in practice. We're going to walk through a few function calls, step by step, and watch how our hash table makes all the decisions for us.
All right, let's trace this thing. Call 1. Message, foo, arrives at timestamp 1. Our table's empty, we've never seen foo before, so we print it, return true. Then, right away, we update our table. Foo is now blocked until timestamp 11, which is 1 plus 10. Call 2. Bar arrives at timestamp 2. Also a new message. We print it, return true, and update the table. Bar is blocked until timestamp 12. Call 3. Uh-oh, foo is back at timestamp 3. We check the table. Foo is blocked until 11. Since 3 is way less than 11, the result is false. No print. Calls 4 and 5, same logic. Bar at timestamp 8 is before its cooldown of 12, so false. Foo at 10 is still before its cooldown of 11, so that's also a false. Now the fun one, call 6. Foo arrives at timestamp 11. We check the table. The rule is greater than or equal to, so 11 is perfectly valid. We print it, return true, and of course, we immediately update the table. The next time foo can be printed is now timestamp 21. See how that works?
So we've seen that it works. It's logical. But why is this considered such a good solution? Well, the answer comes down to its incredible efficiency.
Let's break down why this is so powerful. First, the time complexity. It's O of M, which is a fancy way of saying constant time.
It basically means our check is instantaneous. It doesn't matter if we have 10 unique messages in our memory or 10 million. The lookup takes the same tiny amount of time. It never slows down. Second, space complexity is O of M, where M is just the number of unique messages. Our memory only grows as the variety of messages grows, which is a fantastic trade-off. And that really brings us to the core lesson here. Choosing the right data structure, in this case the hash table, turned a potentially tricky, slow problem into a simple, blazing fast lookup.
And that's really the beauty of it, isn't it? We didn't need some super complex algorithm or a bunch of different data structures. The whole shebang, remembering, checking, updating, is all handled cleanly and efficiently by one simple hash table. It's just a fantastic example of elegant, simple design. And I want to leave you with a final challenge, a little food for thought. Our whole solution assumed that timestamps always go up. But what if they didn't? What if a message from timestamp 5 arrived after a message from timestamp 15? How would that break our logic, and how could you adapt this solution to handle it? It's a really great next-level problem to chew on.